right, next video in limits. This is about limits and continuity. So this is a super important part of calculus. Very often we have to be able to talk about continuity. So we're going to have a lot of theorems that require functions to be continuous, and we have to show that in order to use them. So it's just a really important concept to be able to talk about things being continuous, and there's a formal way to do that. We know how to do it, and we'll talk about that first, like from a graph, but we're also going to talk about the more formal way we would say that something is continuous. So looking at a graph here, and just looking at what's probably needing to be true to define something to be continuous. So let's look at the graph and talk about what things that we know have to be true. So if I just look at a few various places, then I would know that, for example, right here would be not continuous, and the reason it would be discontinuous is because it isn't defined. There's no function there. So one thing that must need to be true is f of c must need to be defined. Okay, so there has to actually be a point there. So it has to be defined for a certain value. So another place that we have a discontinuity would be right here. Well, the problem we have here is if you take the limit from the right and the limit from the left, clearly you get two different things. And so there's a problem, is that we don't have a limit that exists. Okay, so at that point, our limit doesn't exist. So the limit as x approaches some c, wherever we are, of the function, apparently, it seems, needs to exist. Okay, so the limit has to exist. Well, if we look at another place, so here's another discontinuity right here. Well, it's discontinuous, but the function's defined. It's defined weird because it's defined down here, but it is defined. So it has a function value at -3. And the limit from the left and the limit from the right both come together and they equal 5. So the limit exists, but we still see that there's a discontinuity there. So the problem is the limit exists, the function has a value, but those two things aren't the same. So that's going to be our third criteria, is in fact that the limit that we know exists must in fact equal that function value at that same place. So this is our very formal definition of continuity. So for a function to be a point to be continuous on the function, these three things must be true. So if we look at this next table, what we're going to look at here is we're going to answer for that graph all the different things that we can see. It's to find out whether it's continuous or not. So if we go back to the graph, now you have the graph in front of you, so I'm not always going to flip back to the graph, but if I go back and look at x equals 9, what this table is asking me is things like the function value, left-hand limit, right-hand limit, general limit if it exists, and then is it continuous. So let's just go back and look here at x equals 9. So x equals 9 is right here. So if I look at x equals 9 and think about what it's going to ask me, it's going to ask me for the function value, which appears to be about 3.5. My left limit is 3.5. My right limit, however, does not exist because there isn't anything over there. There's nothing on the right side of 9, so I can't approach 9 from the right, which means my general limit doesn't exist. And so our answer for is it continuous there, well, we're going to discuss that. Okay, so that's going to be a different thing. So function value appears to be about 3.5. From the left, my limit is 3.5. From the right, my limit does not exist, which means my entire limit does not exist. And so now the question is the function continuous at x equals c? Well, if you look at the graph, look at the picture, well, it sure looks continuous. I have a point there. There's not anything missing. Well, what we would say is, I'm going to say yes, but I'm going to kind of put a star there. Yes, but technically, we have to be a little careful. It is continuous, but it's an endpoint. So there's a little bit of difference for the rules of continuity if we have an endpoint, because I don't have another side. So as long as I'm continuous from the left and my function value equals that, we'll say it's continuous on an endpoint there. Okay, so next it's asked us to look at x equals 4. So we're going to look at x equals 4 real quick. So at x equals 4, well, at x equals 4, there's a vertical asymptote. So let's go ahead and answer these questions. Well, what's the value at x equals 4? Well, it does not exist. There is no value there. The left-hand limit, so when you went from the left-hand side of 4, we can see that nothing happens because the graph stops right here at 3. So there isn't anything at 4. So from the left, I can't approach it from the left. Now from the right, the function does this and continues on up. So I do have a limit from the right, which is infinity. So from the left, I have to say the limit does not exist. The right limit is infinity, but that clearly means the overall limit does not exist, because remember, left and right limits must be the same and they must be numbers. And we don't have that, and definitely not continuous there. So let's look at x equals 3. So at x equals 3, that's what I actually have circled right there. Clearly, I have a left limit, I have a value at c, but I don't have a right-hand limit, and I don't have a general limit, okay? So here, we're going to say that their value at 3 is 9. The left limit is 9. That one was okay, but the right limit does not exist. The overall limit does not exist. And here we're going to say no. Now, technically, I'm going to put an asterisk by this one too. So those are things that we sometimes would have to discuss, because it's also kind of an endpoint, okay? But basically, the function itself does end at that place. It's not continuous. If our function's domain is to go from -9, not including, and then go all the way to 9 inclusive, then definitely there's a discontinuity right here, right? This whole thing is blank. There's nothing there, actually all the way to 4, right? There's nothing there, okay? That's a little different than here on the end point, because that's the end of where the function is defined. So I'm not going to make a huge distinction about that. We don't have that come up very often where we have to worry about it, okay? So I'm not going to worry too much about endpoints. You need to worry about other points more than you need to worry about that. Okay, so let's look at x equals 0. So if you look at your graph at x equals 0, you've got a point right there, left and right limits, everything's all good. So this is a normal 6 is the function value, left limit 6, right limit 6. So at 0, you also get 6, and it's definitely continuous there. Now, let's look at x equals -3. So when we're at x equals -3, remember there is a function value. It's -6. There is a limit from the left and a limit from the right, which are both 5. Okay, so our function value is -6. That's where the dot is, the filled-in dot. Limit from the left is 5, limit from the right is 5, so the limit at -3 is 5. But because those don't match, the answer is no, it is not continuous there, because the function value and the limit do not agree. So let's look at -5. So at -5, we have a left limit of -2, a right limit of 7, and the value, the function value is -2. So your function value -2, look at your graph as you approach -5 from the left, the function is heading to -2. From the right, the function though is heading to 7, so this limit does not exist, therefore not continuous, okay? All right, so the 3 properties are what are super important here. That's how we're going to identify whether things are continuous. All right, so continuity is important because limits tell us what we are trying to get to, okay, where we may or may not have made it there, but the limit is like, that's where we're trying to go. It's kind of like if you were trying to go to Starbucks, but when you get there, the door's closed, so you can't actually go inside, but you still made it to the place you were going to be. Well, continuity guarantees the door's open, we actually made it there, okay? So we actually got in and we made it through. So continuity is important for functions, okay? So we have to talk about that a lot. All right, so we have different kinds of continuities. These were talked about in pre-calc, but we want to get even more formal with them here. So we have different types of discontinuities. We have what we call removable discontinuities and non-removable. Now, just because something's removable doesn't mean it's not a discontinuity. Often students get that confused. They're like, oh, well, we'll just remove it. No, it can be removed. That doesn't mean that it is. Now, by removable, think of it like all I have to do is fill in a single hole. So think of it like a street. If I drive down a street and there's a pothole in it, I can still go down the street. That doesn't, I'm going to hit a pothole, but if somebody comes and fills in the pothole, the street is exactly the same as it was. It goes in the same direction. We have not changed anything. Take a different situation and say there's an earthquake, okay, and a street has an earthquake or a sinkhole happens or something, and the street suddenly splits and starts, and now it doesn't connect anymore. Well, if that's the way the street is, if I want to fix that discontinuity, I'm going to have to completely rebuild the entire street. So it won't be the same thing anymore, okay? So that's the difference. That's what non-removable is. So removable discontinuities, you have a limit, okay? You have a hole in the graph. The limit from the left and right exists, and they have a value, but there just isn't a function value there. A non-removable is you're going to have one-sided limits that exist, and maybe both of them, but this limit exists from the left, limit exists from the right, but the main overall limit does not exist because they are going two different ways. An infinite discontinuity, at least one side of that discontinuity, your graph is going to infinity. So your limit doesn't exist, which is the same as going to infinity. We just normally describe it as infinity. But a limit means a value, okay? Another way to think about that is if I shoot a rocket off inside the building, I actually have a limit for that rocket because it's going to hit the ceiling, right? So the limit's going to hit it. And I don't mean like a NASA rocket, but like a little paper rocket, okay? If I shoot it off, it's going to hit the ceiling. It has a limit. There's something there. There's a value there. If I shoot it outside, then I don't really have a limit. It can go as high as it can go. Nothing's going to stop it. So infinity is the same as the limit doesn't exist, okay? But it's a better description. So we typically use infinity to describe it if we can, okay? Where this limit not existing, for example, at 1, the reason is because the left and right limits are different, okay? The limit not existing here at 0 is because the left and right limits go to infinity or minus infinity, okay? But these are your 3 different kinds of discontinuities. So basically you have a hole, you have a jump discontinuity caused by left and right limits being different, and then you have infinite discontinuities because one side at least has a infinity. All right, so here we're going to write down, we want to write all the intervals where the function is continuous. So another important thing in calculus is making sure that you know how to use interval notation. Because we're going to use it all the time, you have to be able to read it, and it's also faster. So we want to try to use interval notation whenever possible. So since these do not have arrows on the end of this graph, so here and here, we're going to say that those they are open on the ends there. They don't have open circles on them, but they don't have arrows either. So they don't continue on, and they don't have points. And so for this, we're going to say that, and then also notice it says -5 to 10, not including the ends, okay? So those are open on the ends. All right, so we're going to list where it's continuous. So to start listing where it's continuous, we just work left to right. So it's continuous as I go from -3 until I get, from -5 until I get to -3, and then clearly there's a discontinuity. So -5 to -3, not including -3, so parenthesis. Union, it's also discontinuous. Actually, I'm not going to use union. We're just going to say where the function's continuous. We're going to give all the intervals. So -infinity to -3, and then it's continuous from -3 all the way to +3, not including 3. So -3 to 3, and then it's also, if you go from 3 until you get to 5, but there's an open circle there, so it's continuous from 3 to 5, and then if you go from 5 to 7, and then once you get to 7, you have a jump discontinuity, and then it's from 7 to 10. So notice that all of the ends of those are parentheses, non-included, because that tells me by looking at that interval notation, it's discontinuous at -3, at 3, at 5, and at 7. I can see that by looking at that those are the only points that are not included. Everything else is. So then it wants us to list the discontinuities. And then we're going to go ahead and name them. It doesn't say to name the kind, but we're going to go ahead and do that. So we want to list the points where it's discontinuous. Now, when we list the points, normally when something says list the point, you should give an ordered pair, but we're just going to give the x values of those places. Now, as you get through calculus, you'll see that we have to start being very specific. So normally if something said a point, I would list an ordered pair, but the more appropriate way to ask this question would be give the x values at which the function's discontinuous, because obviously if there was an asymptote, I can't list a point, okay? So we're just going to list the x values. So we have definitely one just going left to right. We obviously have a discontinuity at -3. And then what type of discontinuity is it? Well, it's a hole in the graph, and we would say it is removable. Okay, again, very important to be able to distinguish the types of discontinuities, okay, because that's going to matter a lot later when you do things, okay? So next discontinuity, we keep going, and we see that we have one at x equals 3. And at x equals 3, we have a vertical asymptote. We can see that. It's not drawn in. Remember, asymptotes are not real things, so you can't see them. So you just have to visualize that it's there because you can see the behavior of the graph. So you know there's a vertical asymptote there, and that would be non-removable. So again, that's equivalent to I can't remove that discontinuity without completely changing the graph, because the graph is going up to infinity. I can't get rid of that discontinuity without rewriting totally the graph looking different. The other thing to remember about a hole in the graph is that it's only one single point that's missing, and points actually have no dimensions. They have no width. So if I'm just missing a single point, it's kind of like not a big deal. I mean, it matters that it's not there, but it's not a big gaping thing that, again, changes everything, okay? It's a single point. We also have x equals 5, and that is going to be a simple point discontinuity again, or a hole, and that is removable. And then we also have a discontinuity at x equals 7, which we call a jump discontinuity, and it is also non-removable. So we cannot remove. So the easiest way to remember is holes can be removed. I can fill a hole in. It's a smaller discontinuity. It's not as big of a deal. Still there, still a discontinuity, but it's not as bad. Okay, one-sided discontinuity, or continuity. So this is what we would kind of talk about for an endpoint. Okay, so for example, if we go back to this endpoint on this first graph, and where we were talking about it being continuous, and I kind of put an asterisk. Well, it is what we would call left continuous, meaning it's continuous from the left, okay? It's just not continuous everywhere, okay? But it is continuous from the left. So we could say that a function is left continuous because the limit from the left does in fact equal the function value. And similarly for right continuous, okay? So that's why I kind of put an asterisk there and said an asterisk because, yeah, it's what we would call left continuous, okay? So endpoints are kind of a little different. Now, when we talk about continuity at a point, we would say that a function is continuous at a point x equals c if we have a function defined on an open interval that contains c. In other words, there's stuff from the graph on both sides of C. So it's an open interval. And we would say that x is continuous there if the limit as you approach that point does in fact equal the function value. All right, continuity on an open interval. So we say it's continuous on an open interval as long as it's continuous on every point inside. So a function might be only discontinuous on endpoints because the function just doesn't go past that. So we would just say it's continuous on an interval, an open interval. If it's continuous on a closed interval, it means it's continuous on the open interval and then also continuous from the left at the right endpoint and from the right on the left endpoint, okay, as you can see in that picture there, okay? So as long as we're continuous from the insides and the inside is continuous, we would say it's continuous on a closed interval. So those are just real specific things. Now, sometimes when we need to be able to state that something is continuous, it's nice to be able to say, okay, certain things we just are going to all accept they're just continuous, okay? Like polynomials. So later when you have a theorem and you need to say, hey, since the function is a polynomial, it's therefore continuous, therefore I can use this theorem, okay? Polynomials work. Polynomials are continuous. Rational functions, they're continuous everywhere except where the bottom is 0. Okay, so that's another one. I can just say, hey, it's rational, so it's continuous everywhere except, you know, whatever values on the bottom, and I'm covered. X to the 1 over n, which would be your roots, it's going to be continuous everywhere as long as the root is odd. So you have like x to the 1/3, which would be third root of x. And then it's continuous from 0 to infinity if n is even. So square roots, fourth roots, those are all continuous from 0 to infinity, including 0. Sine and cosine, these are the main ones that I would focus on. Sine and cosine, you can just straight out say they're continuous. They're just always continuous. Exponential functions are continuous as long as you meet the properties of that. Logs are continuous everywhere, basically on their domain. Okay, so as long as you're in the domain. Inverse functions is something we can worry about at another time, but it's continued as long as inverses, you switch domain and range, and so that's where we could talk about that. That's not the biggest ones. The main thing is, hey, here's a bunch of stuff that I can just say, hey, it's continuous, okay? And here's some properties of continuity. If you already know you have two functions that are continuous, if you multiply a function by a scalar, which means a number, still continuous. If you add or subtract two continuous functions, the product or the sum is also, or difference, I mean, sum or difference is also continuous. If you multiply two continuous functions, still continuous. If you divide, still continuous except where, of course, you would make the bottom 0. And then composite functions would be continuous in a little bit more longer way to talk about it, so we can just talk about those when those composite functions come up, as long as certain things happen. Okay, so that's a little bit more involved. All right, so again, here's your definition of continuity. And to prove something's not continuous, all you have to do is show the one of those three things it doesn't meet. As long as if it doesn't meet one of those three things, it's discontinuous. To prove it's continuous, you would have to prove all three things are true. Okay, but if I just want to show something's not continuous, any of those things don't work, done, not continuous. All right, so here we're going to talk about these three places at -3, 3, and 7, and we're going to show whether it's continuous or not continuous at those three places, basically. Okay, so first it tells me to find three things and then say continuous or not. Okay, so C equals -3, so let's start there. So f of -3, it asks me to find f of C first. So looking at the graph, f of -3 equals 2. Again, it's the dot. Okay, it's the point on the graph. F of -3 is 2. Let's do the limit from the left. So the limit of, and I don't need to say C from the left, sorry, I know the value of C, so I'm doing x approaches -3 from the left of f of x. So as I'm on this graph coming from the left, I can see that my limit is -1. And if I do the limit from the right of -3, I also get 1, or -1, sorry, because I'm coming from the right. And so the reason we can say, hey, it's not continuous is, so our conclusion would be it is not continuous at x equals -3, and then we have to give a reason. Well, our function value exists, the left and right limits exist, but the problem is the left and right limits don't equal the function value, or the limit doesn't equal the function value. So that's what you say. So it's not continuous at x equals 3 because the limit as x approaches -3 of the function is not the same as the function value. So now I've proved that it's not continuous there, okay? And so I just have to show the one reason, and then that's it. Oh, well, we're supposed to do all the rest of these, so let me fit these in here. So next we're going to do C equals +3. So we go to +3 and we answer those three things. So f of 3, well, what is f of 3 if we look at this graph? Well, there isn't anything at f of 3, so the function is undefined, okay? So don't put an equal sign, erase the equal sign, and write the word undefined. You can't equal undefined, that doesn't make sense. So f of 3 is undefined. If I do the limit, because it told me to go ahead and find these, the limit as we approach 3 from the left of f of x. So if I go up here and look at 3 from the left, I go to infinity. I'm going up, and I'm also doing the same thing from the right. So I do the limit as x approaches 3 from the right of the function. I also get infinity. And so that's a lot of stuff that tells me this is not continuous. So it is not continuous for any of those reasons. Actually, all of those reasons don't work. So it's not continuous at x equals 3 because either f of 3 is undefined. That's one reason. Or you could say the limit as x approaches 3 of the function doesn't equal the function value, certainly, because the limit doesn't even exist. So you could also just say the limit doesn't exist. I mean, any of those things would be a reason that it's not continuous. So let's do C equals 7, and I'm actually going to just do it right here. Okay, so when we have C equals 7, function value of 7 is where the dot is, so that would be 3. The limit as x approaches 7 from the left of the function is 3. The limit as x approaches 7 from the right of the function is 6, though, looking up there. So this is not continuous at x equals 7, and really the reason here is because the limit as x approaches 7 of f of x does not exist. And again, don't put equals, just say does not exist. It doesn't, I could just, that's another reason, because the limit has to equal the function value, but the limit doesn't even exist. So obviously it doesn't equal that. All right, we're going to just do one more thing here, and then the rest of this will be for class in order to finish that, and that's how to remove them. So we're going to talk about A and B here on how we would describe the function and where they're discontinuous, because this is stuff that we've done quite a bit. We're just going to use the knowledge that we just talked about continuity to answer the question. So for A, well, we know that at x equals 3, we have a discontinuity because this is a rational function. If you plug 3 in to f, you know, or to x, the bottom will be 0, top is not 0. So we know for a rational function, that means this is a vertical asymptote. So that means if I do the limit as I approach 3 from the left, and I do the limit as x approaches 3 from the right, I know I'm going to get an infinity of some kind because there's a vertical asymptote there. And if you remember from a previous lesson, it's really easy to figure that out. I know that both of these limits are an infinity. They're either both positive, one negative, or both negative. There's no other option because I have a vertical asymptote here. So all I have to do is pick numbers that are very, very, very close to 3 from the appropriate side. Tell me if they're negative or positive. So as I approach 3 from the left, like take 2.9. Well, if I plug 2.9 in, I'm going to get negative on the bottom. That means that side is going to negative infinity. If I plug in a number really close to 3, but on the right, like 3.1, 3.1 minus 3 is positive, so this side must be positive infinity. Again, I already know it's an infinity. I just need to know what sign it has. Okay, so then if we want to describe the type of discontinuity and justify it, the fact that both of those limits are there, I would also, and I also know f of 3 is undefined, of course, because I can't divide by 0. So I have a vertical asymptote at x equals 3, and this is a non-removable discontinuity. I am determined to put an E in there, sorry. It's a non-removable discontinuity, or an infinite one, okay? So we still use all the stuff that we know. Now for g of x, I'm going to need to factor this in order to figure this out. Will make it easier. So remember again, if you are not good at factoring, you need to become good at factoring because we use it a lot. So I need factors of 12 that add to 7. So that's going to be 3 times 4. My first terms have to be 2x and x. That's the only way I'm getting 2x squared if I'm using integers. And then my outside product and inside products, the number parts have to be these two things. So that means this has to be plus 2, so that my outside is 4, and that makes this 3. If you need review of that, please work on it. Now, this time the difference is the discontinuity at -2 is removable because the bottom and top are both going to be 0 there. So at x equals -2, we have a removable discontinuity. In other words, we have a hole in the graph, okay? And then our reason that this would be a discontinuity as far as meeting the criteria is that if we took the limit as we approached -2, we would get an answer, and this one was called G. We would actually get an answer, and the answer that we would get is easy to figure out because remember, you can cross those factors off. Don't do it now because then an equal sign would be wrong, but think about, imagine crossing them off, plug -2 in, and you're going to get -1. So that means that limit is -1, but the function value does not equal that. So the limit as I approach -2 does not equal the function value at -2 because the function in fact, oh sorry, G is -2, the function in fact doesn't have a value, so it can't be equal. All right, so the last examples are examples that we can cover in class, but that should give you a pretty good idea about continuity.